All right. Hopefully my slideshow works. Did it flip to the next slide?
Yes.
Oh, good. Yeah, I'm just trying out something different here. So, yeah, tonight I want to talk about space weather. You know, it's mainly dominated by the sun and our magnetosphere. But first, I want to talk about the James Webb Space Telescope. You know, they've just been sending back just amazing, beautiful pictures, just incredible things they're finding. And this was one that came out about a month ago, the Cartwheel Galaxy. It's about 500 million light years away, and they suspect that the structure of this galaxy is due to a high-speed galactic collision. It's not shown in this frame, but further away is another galaxy that's speeding off that in the direction they think it was the culprit that smashed through it and caused this. In the composite image, there's two cameras, the near infrared, the near cam, and then the MIRI, which is the mid infrared. The near cam is in blue, orange, and yellow. And that smooth core shows some dense dust and older star populations. But when you look at the outer ring, it's kind of clumpy, and those clumpy shapes show some younger stars and supernovas. And then the MIRI data is red, and that shows some silicate dust and the hydrocarbons and spokes. So with the James Webb, they can see much more detail than they could with the Hubble, because the James Webb is much deeper into the infrared, so it sees new details. But, you know, in the background, and you've probably seen these pictures on the internet, in the background, every time there's a picture, there's just galaxies everywhere you look, galaxies everywhere you look. So this next picture on the right side is, it just compares Hubble with James Webb. Hubble can see this far back in the past. Hubble has infrared, but it's a small one. James Webb can see much further back into the past. So theoretically, it can see earlier galaxies. And what they've been finding out is James Webb is seeing many more, and the galaxies they see are more mature than what they'd predicted. And all it means is the theories of galaxy formation need revising, because some of these theories are ad hoc. Nobody was there when it started, and so they have to modify the theory. So it's an exciting time to be an astronomer. They're seeing these things. And related, you know, the galaxies they see further back, and it's related to the Big Bang and the theory of how things started. And I want to put this quote up here from Sabine Hassenfelder. She's a theoretical physicist. She's in Germany. Her specialty is quantum gravitation, and she has a YouTube channel. So here's what she says, and it was just about a month ago, and she said this in response to some of the James Webb images of galaxies. She said, "Now most physicists, me included, think that the Big Bang singularity is a mathematical artifact and not what really happened. We should be using a better theory, one that includes the quantum properties of space. Unfortunately, we don't have the theory for this calculation. And so all that we can reliably say is, if we extrapolate Einstein's equations back in time, we get the Big Bang singularity. We think that isn't physically correct. So we don't know how the universe began. The Big Bang is the simplest explanation we know, and that is probably wrong. And that's it. That's all that science can tell us." So I was glad to see that. It's kind of refreshing. She's a no-nonsense physicist. She doesn't have to compete for funds and toe the company line. She can say what physicists are really thinking. And so Einstein's equations are for general relativity. It's the gravitational theory that describes how things move in the universe in response to gravity. And it's just basically a set of differential equations. But Einstein's equations don't specify the initial condition. They just say it's descriptive. It just says how things move. It doesn't say how things came to be. And so the Big Bang is the hypothesis of how things started, because something had to get started, because when you run Einstein's equations backwards, everything collapses. So then the singularity is when you get into infinite density, infinite pressure, and heat and all that, and all the theories break down, just like in a black hole. At this black hole singularity, our current physics breaks down. So she's just saying the Big Bang's the simplest explanation we have, but it's probably wrong. It's an ad hoc theory, and as we get more data, they can modify it and learn more. So again, exciting times to be a physicist. We've already talked about the feed schedule, and it sounds like weather holding, there'll be several people down there at Haswell this Sunday, October 2nd, and we'll change the feed. If there's time, one thing Ray and I would like to do as well is get up in the dish and measure the diameter of the dish, measure the focal distance. We've wanted to do that for a while. So if you want to get up in the dish, we may be trying that Sunday. After the 2 EME weekends, totally depending on Artemis launch, my vote would be to put the 1420 up, put up Ray's 1420 feed for a while. We can do pulsars with that and hydrogen, and we can do, the Lewis and Glenn can do Mount Cal, and they can do the raster scans, that they demonstrated there at the open house. It's a very exciting new capability to do the raster scan. At 1420, they could do calibrated objects, so that'd be fun to see. But we'll see. We'll see if we get through October, November, and when the launch actually happens. I did want to mention HAARP is going to do a lunar echo. They've done that before. They're going to do a Jupiter bounce. They've never done that. So October 22nd to 28th, and between 2.7 and 9.6 megahertz, it's going to be CW coming from HAARP up in Alaska. They're going to be bouncing off the moon and bouncing off of Jupiter. The moon should be easy for anybody to hear. This is something you can do at home with your HF antenna. You should be able to hear that on a dipole or whatever you have. Jupiter is a different question. Nobody knows if they'll be able to hear it or not. So if somebody's at Haswell this time, you could try the 80 meter or 160 meter antenna just for fun to see if we could pick up the moon or Jupiter there on CW from HAARP. So what I want to talk about is space weather, PSWS. It officially stands for the Hamsai Personal Space Weather Station. It can also stand for the Plishner Space Weather Station. So I'll be talking about both here. And I know that some of you guys know way more about space weather than I do. So if I say something naive or wrong, jump in and correct me. But basically, space weather is how the sun affects the Earth's atmosphere, ionosphere, and the technology, our GPS satellites, our power grid, and all those things can be impacted by severe solar storms. And then this just shows the ionosphere layers, F, E, D, the different layers. And most of you, I think, have seen this or you've used it in your ham radio, or at least you had to look at it when you went and got your ham license. What kind of things can we actually observe? You can track sunspots easily just with some coded binoculars, or there's lots of fun websites. The Space Weather Prediction Center at NOAA has a great website. They got a ton of information. Everything you'd want to know is on that website for space weather, all the reports from the satellites and ground sensors. One thing we can do, already doing, is SIDS are the sudden ionospheric disturbances from X-ray solar flares. We can track those at VLF with the SuperSID antenna. And that data all goes to Stanford, the solar center there. At HF, we've already used it, and we showed earlier this year several instances when, with the radio jove setup we have down at Haswell, we can detect solar flares and correlate them with the Stanford data. We can also detect wideband solar radio noise bursts. So the radio noise bursts sometimes are caused by the solar flares, and often they're just caused by around 20 megahertz. They're caused by in the chronosphere itself, separate from a solar flare. And that's using radio jove 2.0, and that's a wideband. It's roughly 16 to 24 megahertz using a spectrograph. And I'll show that here later as well. Another thing we can do is measure geomagnetic storms here on Earth with a magnetometer. I think the group already has one of Whit Reeves' SAM3 magnetometers that we could deploy. One thing I'm tracking is the Hamsai product. And so Hamsai, the New Jersey Institute of Technology designed it. Taper in Tucson, the group down there is building it. It's based on the PNI RM3100, so it's a 3-axis sensor. And I'll talk more about that in a few minutes. We can also track the 10.7 centimeter radio flux. That's 2 gigahertz. That correlates very well with sunspot activity. We get daily reports from Canada, and Ray, when he did his presentation a couple of months ago, talked about his dish and the progress he's making on doing the radio flux. And then lastly, we can also monitor various ionospheric disturbances. SIDS, I talked about. TIDS are traveling ionospheric disturbances. So TIDS can be from, they can be as large as, say, 1,000-mile traveling wave down to hundreds of miles. So they're large traveling waves in the ionosphere. There's some ways to monitor those. One is use the GPS satellite, get the total electron count. You get tech from the difference in the phase delay from the 2 GPS signals. So each of the satellites actually downlinks 2 frequencies. It's called L1 and L2. And you can do the phase difference on the phase delay difference on those to get the total electron count. Total electron count correlates very nicely over the years with the 10.7 centimeter radio flux. Another thing we can get from GPS is called the S4 scintillation index, which is exactly what it says. It measures the scintillation in the ionosphere, and it's the ratio of the standard deviation of signal intensity to the average intensity. And I'll show examples of that. At HF, you can monitor the time frequencies, WWV and CHU in Canada. You can monitor those for Doppler shift. And when the electron density in the ionosphere changes, that causes a change in the transmit and receive ray path. And so that Doppler shift change is measurable. And then many of you have participated in digital ham radio, and you've sent your reports to either PSK Reporter, or if you're doing F8, FT8, or Whisper to WhisperNet, or the reverse beacon network. These databases have turned out to be a treasure trove for researchers, because they'll go back and they can find years of data that's very carefully documented in terms of the transmitter location, the receiving location, the exact time, and the frequency, the strength of the signal, and those things. So they are doing data mining here and helping them understand ionosphere. The Hamsai group, I know Rich and others have been participating in some of their meetings. Their goals are to deploy a network of ground-based sensors to better sample the space environment. So obviously we have a lot of satellites doing sensing of the space environment, but those are at the global level. And then a lot of universities and governments have sensors scattered around, but those are at the 1,000-mile level. There's nothing at the 100-mile or 10-mile grid. And so they're really trying to get more sensors scattered around to better understand the space environment. Some of their goals, they want to better understand the impacts of solar flares, including on radio wave propagation that affects us. They want to understand the geomagnetic and ionospheric storms, better understand the internal electrodynamics and variability of the ionosphere. It's not totally understood yet. They want to understand the sources of these medium and large scale traveling ionospheric disturbances, the TIDS. And the sources are called atmospheric gravity waves. Atmospheric gravity waves that disturb the ionosphere are caused by earthquakes, volcanic eruption will cause it, a tsunami, and even a rocket. When Artemis goes off, it's a big rocket. It's going to cause an atmospheric gravity wave that's going to cause some traveling ionospheric disturbances. How far they go, how far they can be detected, I don't know. And then they also are trying to understand better the causes of sporadic E. Now, their current status, the Tangerine is a custom SDR, and that's one that we've been tracking and hoping to get, but it's on hold for an ongoing FPGA chip shortage. So I don't know when that'll be available, or even if. This was going to cost around $1,000, and at the same time, they were doing something they called the Grape, which was a low-cost PSWS, and this one was targeted for around $300. It's just going to do the Doppler shift we talked about. It's got 4 16-bit simultaneous channels, ADC channels, synchronized sampling at 1 PPS. They're using the new generation U-Blocks GNSS for time and frequency. They're using GNU radio on a single board computer, and what they found out so far is Raspberry Pi 4 is not going to cut it. The Raspberry Pi 4 can handle 4 16-bit simultaneous channels. So they're looking at a higher powered single board computer. These are the channels they're going to be doing: 2.5, 5, 10, and 15 megahertz for WWV. And then for CHU, it's going to be 3.3, 7.8, and 14.67 megahertz. And they want to do, each station would be doing 4 of these simultaneously. All of it goes into a central database where they can research it. This is a Hamsai group. Dr. Nathan Frizzle at University of Scranton runs it, and most of this work on this GRAPE unit is being done at Case Western Reserve University. They have a National Science Foundation grant to produce 30 of these boards. They're working on them. Now hopefully we're in line to get one of them, and they should come out late this year, early next year. They're based on CMOS logic gates. They have to be available by about a year from now, because Hamsai is already planning for the next 2 solar eclipses. So 2023 in October is a partial solar eclipse. It's an annular. It's going to be about 90% annular. If you want to see it, just go down to 4 corners. And right here in the Springs area, I think it's like 84%. Out at Haswell, it was about 80%. And so they're going to be doing experiments similar to what I think Rich did 2017. They want to do that with the partial in 2023, and then certainly in the total eclipse 2024, in April of 2024, when it crosses Texas and those places. So this GRAPE unit will be ready for those. I mentioned all this because in our grant that Myron mentioned earlier, we did put in funding request and got the funding, and haven't spent any of it yet because we were going to get a Tangerine. They're not available. We might get a GRAPE, and so this funding we're just going to hold until we need it to purchase some of the sensors or antenna equipment. So that was the Hamsai PSWS, and now about what are we doing at Plishner? Well, for the operational sensors that are already there, we have 3 super SIDs. Floyd Glick has one in the Springs, Rich Russell has one in the Springs, and Ray Uberecken has one. In parentheses on these, I try to mention who the sponsor is and where the data repository is. So Sarah is a sponsor. Stanford Solar Center is where all the data is. You can get that. ScintPy is this brand new one. We just put it up last month. I'm going to show some examples of it. It's the one doing the GPS scintillation measure. It's sponsored by the University of Texas at Dallas. They have a National Science Foundation grant for it, and they also hold the data. We also have Radio Jove 1.0, sponsored by NASA. It's using the Flex 1500 SDR at 20.1 megahertz. And so all 3 of these can be used to detect solar flares and some solar radio burst. What we plan on doing is upgrading Radio Jove. Radio Jove 2.0 is the wideband version. And all we need to do is add SDR Play. It's the RSP1A. And I'm testing one right here. And we add the spectrograph software. So Jim Sky at Radio Sky developed a spectrograph and put that out for free for the community to get more involved in this. And one thing we may do is run both of them at the same time. Run the narrow band on the flex and run the wide band at the same time. They both have advantages. The only thing I'm still haven't sorted out yet is the antenna for this. The dual dipole antenna was designed for narrow band. I don't know how well it'll do on the wide band. It should pick up, most of it, but we'll see. Then for the ground magnetometer, this has already been designed and built. They've built 300 of them. There's a ham operator, part of Taper. He's testing them now. So they may be available in the next few months. And I think we'd like to get one of those. It may be more of a beta, so it may need some little extra care at the beginning, but then it'll just be putting a hole in the ground and reporting data. And then whenever GRAPE comes out, we'll get one of those and deploy that as well. So we'll have more sensors collecting more data, and these will all be part of either NASA or these various university research projects where the data all goes and they can learn more about the ionosphere. So scintPy is this dual frequency GNSS receiver. It looks like this. There's just an active antenna. It's got the U-Blocks receivers, and it just connected to a Raspberry Pi. All this is in a little blue box just in our rack down there, and it's connected to internet. Every night, it uploads the raw data that it collected for the last 24 hours down to Dallas. It just does a FTP, and then we can go in anytime to their server and download the resulting files. So they take the data file, they take the raw data, they process it and generate some intermediate products. The signal to noise ratio, the total electron count, and S4 for each satellite. Well, each constellation has 20 to 30 satellites. So there's quite a few satellites up there. HDF5 is the hierarchical data format used for a lot of science data. And then I just use a Python program to grub through the data and generate some plots and see what we got.
Tell me what S4 is for a satellite. Is that a signal strength?
S4 is the scintillation index. I'll show that in a minute. So S4 is, it's just what they call it. There's various ways of measuring the scintillation in the ionosphere. So basically you're measuring the scintillation between you and the satellite going through the ionosphere. It's measuring the scintillation by using those two frequencies, L1 and L2. So it was a little over a month ago, Mark and Ray got up on that 30-foot tower right behind the communications trailer and installed the antenna. And I had Mark take some pictures. So this is it looking north. It's just on this arm here. That's the antenna. That's the active antenna right there. 30 feet up, looking north. This is looking east, west. Well, of course, south is dominated by the dish. But that's filtered out anyway, so that's fine. So what I wanted to do is I wanted to get some quiet days for baseline. Here on the left is GOES X-ray data. This was 3 days. I just took the middle day here. September 7th, that's very flat, no activity, be a nice flat day. And then for comparison, this is Floyd's SuperSID data from Stanford. This is the nighttime, and then this is sunrise and sunset. So this is daytime here. Very flat, very nice, clean data. So that's what I used just as a starting point for a baseline. This is what scintPy data looks like on the same day. So GPS 5, that's the 5 is the ID number, 18 is the ID number. There's 30, I don't know, 32 of them or something. I run this Python program, it generates plots for each one, and I just flip through them and find some that look interesting. Now, GPS satellites have a 12-hour orbit. They can be overhead as much as 5 or 6 hours at a time. And so I picked some that had at least a few hours. And these two, The first two are the signal to noise ratio. There's two measures of signal to noise ratio because we have two frequencies, L1 and L2. So the black one is the first one, the red one's the second one. And it's just showing that the signal noise ratio is relatively flat at that point. And the next two are the scintillation that Ted was just asking about. So S4 for the first frequency and S4 for the second frequency. This is a measure of the scintillation that is occurring in the ionosphere. And it's completely flat, which is great. This bottom one, the blue line is showing the elevation. So I plotted the elevation of the satellite. So basically, and what I did is I cut off at 30 degrees. Below 30 degrees, I'm not showing any data, because if you looked at the data, what you'd see is like up here below 30, the data drops off on either end because you're going through a lot more ionosphere. So you want the data to be when you're looking more or less overhead, not down low on the horizon. There's a lot more ionosphere. So I trimmed it at 30 degrees. This bottom green line is the actual, they call it the P-TEC, which is the phase total electron count. And this is all new to me, and I don't totally understand the TEC plots. This is what I expect is for TEC to be flat, but in a lot of the graphs, they're not. This is not totally calibrated data. This is more of a raw product from Dallas. They take all the data and they grub through all of it and clean it up. This is more of just a quick look because I told them I want to see what it looks like. Anyway, this is what a normal or what a quiet day looks like, just for a baseline.
So if the satellite is going towards the horizon on both ends, particularly on the right,
Yeah.
I suppose we're looking through more atmosphere, right?
Well, no, I cut it off on both ends at 30.
Yeah, but so you're thinking it would be symmetrical, but it could be like to the south or something is different than the east.
Yes, absolutely. You're right. And this one shows a little bit. The ones I'm showing you look more like this, but a lot of them, if it's up for an hour or two, it may just be some kind of a goofy line because it's way down lower. It's not directly overhead. So you're right. They're all over the place. So what I've been doing is monitoring for solar flares. And on August 28th, we had a couple of nice ones. It was M6.7 here at 1548. These are all UTC times. And then almost 3 hours later, an M4.6. And the interesting thing was the X-ray flux stayed above M1 for like 4 hours. So for an extended time, the flux was above M1. And so that caused some good disturbances. This is the GOES report. This is a Stanford supersid report, just showing the disturbance. I use these reports to make sure I'm using the right time when I go to the scintillation data. So here's what our new GPS data looks like for this same date, August 28th. And this was satellite number 15 and 18, and they both look similar, but you notice here at UTC 18, and that was about in the middle of the, I say the time frame was basically 1600 to 2000 for at least being up in there. So about in the middle of that, we have a significant drop in the signal to noise ratio for both frequencies on both satellites at the same time, 1800. And clearly some disturbances in the scintillation value at the same time on both satellites at the same time. So that was encouraging. That was the first flare that I'd gotten where I'd seen a bunch of others and I couldn't really tell, but this one is clearly correlated with the GOES data, with the supersid data, correlated between two separate satellites at the same time, big drops in SNR and the scintillation index. TEC didn't tell me anything. I don't know if it's supposed to, because they're going to try to use the phase TEC at a finer resolution. They're going to try and use the phase TEC to track these traveling ionospheric disturbances. So I don't have enough data to do that. We're just one point. To track the TIDs, they have to have multiple sensors across the United States tracking at the same time. So we're just one data point. I was just really happy to get something like that, and because we put up that new sensor and we're getting the data, and sure enough, it's reporting the solar flares, the impact on GPS. And I think that what I have, so this is the totally shifting gears. This is the, so that's all for the new scintillation data. And I just got a couple of charts on the radio sky spectrograph. This is for radio jove 2.0. I've got it running at home. I just have a dipole 50 feet up in the trees. It's a long dipole. It happens to be fed off the end. And this was on September 23rd. So and on these spectrographs, time is on the bottom. So this is UTC time. This is only about 2.5 minutes. 2.5 minutes of time along the bottom, and along the vertical axis is frequency from 16 to 24 megahertz. So this is 8 megahertz frequency. All of the horizontal stripes, the horizontal bands, the data, that's all, to me, it's all RFI. It's all the ham bands, it's all the foreign shortwave stations, it's civil service, all the stuff that happens outside the ham bands, and including some of it is the ham bands. So that's all what we kind of expect to see. The diagonal ones, you guys have probably seen these. These are radar sweepers. And then this is the solar radio burst, kind of the feathery, blobby looking thing is a wideband. Solar radio bursts are very wideband. They last a few seconds. This was not a strong one. This was a rather faint one. The stronger ones will cause, shortwave radio blackouts and shortwave radio fade outs. So sometimes on these, when you have a stronger one, then you'll see right away that there's a fade out or even a blackout across the ham bands and across the these bands here. Anyway, that's what a solar radio burst looks like. And I correlate this with the Radio Jove IO group. So it's one of the groups IO, it's Radio Jove, and it's Jim Sky, Dave Topinski, Richard Flagg, and some of those guys are posting almost every day results of what they got, both on recording Jupiter storms and solar radio bursts. So I'll go on there, find something, find the right time, and find the if it correlates. So this was correlated with the Radio Jove group to make sure that I'm not just seeing things there. So that was at 14:55, and on the same day, see, yeah, this was a little bit later. The same day, there was another faint one. Again, I correlated this with the Radio Jove group. So that's what solar radio burst looks like. This is what Radio Jove 2.0 will look like when it's running down in Haswell. Although when it's running down in Haswell, I don't expect to see quite as much traffic on the bands. It should be quieter. There may be some, and the noise actually is not a problem for a solar radio burst, because a solar radio burst will wipe out anything here. That's why we get the fade outs and blackouts. The noise, the radio noise will affect Radio Jupiter, because the Radio Jupiter signals are much weaker. So the Radio Jupiter signals, and I think Ray has seen those on the narrow band, they're quite a bit fainter. So I haven't tried that. I don't think I can pick those up here with my little dipole. We need a better antenna. Anyway, that's all I have for tonight. Any more questions?
So if there was a big radio burst on that picture there,
Yeah.
The horizontal lines would dim as well?
They do, yeah. It's incredible.
Because they might be transmitting, but you just couldn't hear it.
Yeah, and you've experienced that with your ham radio, or if you're listening to shortwave radio and there's a brief fade out, and then the next day you read in the newspaper that there was a solar storm and it caused a fade out or burnout or a blackout. But you'll see everything, including the blue background and all the signals. They will get significantly dimmer, and they even go black on a strong one. I haven't captured any of those yet, but that's what I have seen on the group.
Now, this radio burst actually makes it look like noise everywhere because it's a brighter color, meaning
Yeah,
a stronger signal.
yeah,
So in a big burst, it would be all white and you just wouldn't see this. You couldn't hear the signals in the background or what?
exactly. If you go on the Radio
So
Joe IO
it's more
group,
like a whiteout to us. Okay.
yeah,
In this
but
case.
on a big burst, it'll be so the color is so if it's orange or red, that's a brighter color. So on a big burst, you'll have this big feathery blob that extends out more than a few seconds, and it'll have bright parts in it. And in those bright parts, you'll see that it's just blocking out any other anything else that was transmitted during that time.
Do they have some examples of that up there on the Radio Jove too?
Yeah.
Thanks.
I'll send you some.
Well, I'll find them in time. That's fine.
Yeah. And what the Radio Jove guys do, Tom Ashcroft and some of those, now and then when they get a really interesting one, either a Jupiter or a solar storm on their spectrograph, they post it up on the Sarah listserv. So the Sarah group shows some of these too now and then. It's from the same people.